The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So today we're going to talk about communication networks. Communication networks is a great application of graph theory. So what we're going to study is how do you route packets through networks. So you have the internet, which is a chaotic network. It's not organized. We are interested in highly structured networks. And you can find them, for example, in parallel computers where you want to route the data flow. You can find them in certain telephone switch networks, and so on. So we're going to talk about a few very special ones, binary trees, and then slowly we will figure out what all these performance measures really mean. This one has to do with latency. We have switches, their size, the number of them, congestion. And then we will slowly get down to Bayes' network, which is a really beautiful network with beautiful parameters, and we're going to prove those. So let's start off with the first one, the complete binary tree. And let me draw it for you. In this network, we will have a root. And let me just draw it first. We have vertices that represent here the switches. So these circles, let me explain it over here, actually represent a switch. And the idea is that these actually direct packets through the network. And these packets are fixed-sized packets of data, so like, I don't know, say 4,000 bytes or bits or whatever the network wants you to comply to. So these are fixed-size pieces of data. So what we want is we want to be able from every terminal, and the terminal I will denote by a square, from every terminal I want to be able to reach any other terminal. So what is a terminal? Terminal is like a computer or something like that. It's actually the source and the destination of data. So what we're looking for is how can we find a network of switches that are connected through wires, fibers, or, yeah, that's the question.
The top of the that was getting cut off. That was that one.
Oh, sorry.
Oh, okay. Thank you.
So what we want is we want to route packets that come from any terminal to any other terminal. That is what our goal is, and we want to make sure that that is efficient. So the first one is this binary tree. And let's see how this may work. We may have switches that actually have inputs coming from terminals. And the switches may also output to terminals. These are here at the bottom. At this side, we have a similar structure. This is the root of the tree. We have another switch over here. We go down, we go up here, and once more, like this. And again, we have input coming in or an output coming out to their respective terminals. So what is happening here is that I would like to have an input, say input 0, wants to travel all the way over to, say, the output that is present over here. So let me label these. So we have the output 0, input 1, output 1, input 2, and output 2, input 3, and output 4. So, well, I can definitely reach every single output from any input. So that's great. So this looks like something that you are familiar with, right? It's like just a tree. We have, essentially, it's a directed tree, but I mean, it's a directed graph, but these edges go in both directions, right? So I have an edge that goes from here to here and back from here to here. So this is the kind of layout that you could try out first to see whether this type of network would lead to good performance. So let's have a look at the different parameters and see how well this behaves. So here we have a few parameters that we will be talking about. So first of all, let's talk about the latency in this particular network. So how are we going to measure this? Well, we're going to look at this graph and we're going to measure it by the number of wires that you need to go through from an input to an output. So let me write this down. So the latency is the time that is required for a packet to travel from an input to an output. And how are we going to measure this? Well, we're just going to measure this by the number of wires that we need to go through. So this you have seen before. We can measure this by the diameter of that particular graph. So here we will define it for a network. So the diameter of a network is going to be the length of the shortest path between the input and output that are furthest apart. So let's have a look at the graph above. So for example, we can clearly see that, for example, input and output, so say input 0 and output 1 are connected by just going up one step over here. But just going up from here to here, then this switch forwards the packet to this switch reroutes it, forwards it over here, and then it goes back to the output 1. So for example, this particular path only has 1, 2, 3, 4 edges. And what we're interested in is sort of the worst case time that it requires to go from an input to an output. So that means that we are interested in the diameter. And the diameter is, in this case, well, the shortest path that you can find from an input to an output that are furthest apart. So what are those who are furthest apart? Well, of course you would like to go through here, right? So if I connect the input 0 to, say, output 4, I will need to go all the way up through the root down to the output. And how many edges do we see here? 1, 2, 3, 4, 5, 6. So in this example, we have a diameter that is equal to 6. And in general, if we are looking at n times n network, so what does that mean? N is the number of inputs, and n is also the number of outputs. So in this case, we have a 4 times, oh, this is actually 3 over here. We have 4 inputs and 4 outputs. So this particular example depicted on the board is a 4 times 4 network. So if you generalize this for any size binary tree, say an n times n network, then how many, what's the diameter of this, of such a general network? Well, if we have n inputs and n outputs, well, we have to go all the way up through towards the root and all the way down. So we actually count the length of a leaf to the root here twice. So in general, we have a diameter that looks like this. It's 2 times 1 plus the logarithm of n. So in this lecture, we will have n is going to be a power of 2, just to make calculations simple. And the logarithm is always to the base 2. So this is the diameter of a general binary tree. And well, what are the other parameters? So that does not look too bad. I mean, it's logarithmic in n, so that sounds pretty good. What about the switch sizes? Well, how do I measure those? It's like the number of inputs that get into it and the number of outputs that get out. So in this case, I will have 2 inputs that go into this switch, and there are 2 outputs coming out. So this is what we call a 2 times 2 switch. So this would be a 2 times 2 switch. But if you look at this one, for example, we see 1, 2, 3 outgoing edges and 3 ingoing edges. So this is actually a 3 times 3 switch. And in a general binary tree, we will see that all these intermediate nodes over here, they're all 3 times 3 switches. So the most, the approximately half of the switches are actually 3 times 3 switches. So that's a switch size. Now you may say, well, why don't I use like a larger sized switch? That would help me a lot, right? If I could use, say, a 4 times 4 switch, then I would be able to have more inputs coming in, more outputs coming out, and I can actually maybe use a ternary tree rather than a binary tree. In a binary tree, every node at a level has like 2 children, right? But we could design a tree that has at every level 3 children. So then we can use 4 times 4 switches. If we do that, then the path from the leaf up to the root is getting shorter and the diameter gets smaller. So if I increase sort of the switch size, so rather than 3 times 3, we look at 4 times 4 or 5 times 5, 6 times 6, and so on, then the diameter will actually reduce. So what about having a monster switch? Like I have just one switch, and I have my input 0 all the way up to input n minus 1. And then I have my outputs on the other side. Well, of course, the switch size is n times n, but the diameter is nothing, right? You can immediately go from, the diameter is reduced to 1. You can immediately go from an input to an output through the switch. But this, of course, conceals the problem. So what we're interested in is, well, we're actually really interested in how to solve the problem of routing all these inputs to these outputs using smaller, smaller switches of size 3 times 3 or 2 times 2. What we're really interested in is, what is the internal structure in this monster switch? I sort of have concealed the problem by just saying, oh, I got a big switch. But, you know, what we want to solve today is, how do we do the routing in this case within the monster switch? So we want to use just small switch sizes and build up a network using these smaller ones, like 3 times 3 switches or 2 times 2 switches. That brings us to yet another parameter, because he would like to count the number of smaller switches that we use, and that relates to the cost of the network. the amount of hardware that you need to put into it. So in this example, we have the switch count. Well, it's pretty simple, right? It's 1, 2, 3, 4, 5, 6, 7. We have 7 switches. And in general, if we have n inputs, so 1, 2, 3, 4 inputs, then the number of switches that we use in the binary tree is 2 times the number of inputs minus 1. So let's write that down. So over here we would have 2 times n minus 1, which is the number of switches that you actually use. So how can you see that actually? So in general we have 1 plus 2 plus 4 plus 8 and so on plus n. N is a power of 2 according to our assumptions. And if you add them all up, I think you can check for yourself that this is actually equal to 2 times n minus 1. Okay, so now we have the switches. So far this looks pretty good actually. We use small switch sizes. The number of switches is linear in n. Diameter is logarithmic in n, so that sounds good. So what about congestion? Do you have any idea what's the problem with this graph? What is the big problem here? What can happen in a very, sort of a worst case scenario where the packets get routed from the inputs to the outputs? If they need to go to certain locations, then they may have to travel through the route. So you get congestion over here. We don't like that. So this route is actually then overloaded. Actually, you can already see that if, say, this particular switch, if this switch fails, then actually we will have 2 disjoint trees that cannot even communicate to one another. So this brings us to the idea of congestion. And in order to define it better, you will need a few definitions. So to start, we will define a permutation. And we will use this to stipulate the requirements that we want on how inputs and outputs are related to one another, which input needs to communicate to which output. So permutation is a function pi from the set 0 to n minus 1 to the same set. And it is such that no two numbers are mapped to more than once. So no two numbers are mapped to the same value. So what we really want, to put it in mathematics, right? We want that pi of I is only equal to pi of j. Well, if and only if I is equal to j. So let's have an example to plug into that picture over there. So a first example could be pi of I equals, say, n minus 1 minus I. This is a proper permutation. No two numbers map to the same value. Another one could be the identity permutation, like you map I to the same I. So that's another example. Now, how do we use permutations to go towards the idea of congestion? So permutation can be used to formulate the permutation routing problem. And the permutation routing problem is defined like this. It's defined as follows. What we want is that for each I, we want to direct the packet at input I to output pi of I. So you want to do that for all I. So let's have a look at this particular example, where we look at the identity permutation. So if you do that, we can easily route these, right? So I want to send a packet from input 0 to output 0. So I can simply go into this direction. I just go towards this switch, and it gets routed back to this one. I can go like this, and this one can go like this, and this one goes like that. Now, if you look at the other permutation, the picture looks very different. Now, we want to route input 0 to output 3. In order to do this, I will actually need to go all the way through here, and then all the way down to this particular output. And now the picture gets into a big mess, because for input 1, we have to go to output 2. So for input 1, well, we go all the way like this. We again go through the root, and then we go down to this particular output. And as you can see, for input 2, we need to connect to output 1. So again, we go all the way up, and we go all the way down. And for this one, we will again go all the way up and all the way down to input 0. So now you can see that this particular switch over here has to serve packets from all the inputs. All the 4 packets have to travel through this particular node here. So this leads us to the following definition of congestion. So the congestion before we continue, let me first define a path. So for each I, we direct a packet at input I to output pi of I, and the path that corresponds to this route is actually denoted by as follows. So the path taken is denoted by P I pi I. So now we can define the congestion of a set of such paths. So the congestion of the path corresponding to P0 to P pi 0, and so on, and we go all the way up to the n-1th input that needs to be mapped to pi of n-1. So the congestion is now defined as the number to the largest number of paths that pass through a single switch. So in our example, we saw that in the case of the blue arrows here, which for the identity permutation, well, this switch only needs to transmit 1 packet, and all those actually 0 packets. So actually the congestion here is equal to 1. And for this particular permutation, well, we had to direct all the packets through the root, and that's the most accessed switch, and that switch has congestion 4, right? So the congestion over here is equal to 4. Now this does not look so good, because for a binary tree, we always have this vulnerable root that is right here in the center connecting the left side to the right side. So I can always find a permutation, actually this permutation over here, that leads to this worst case congestion. So what we're interested in is the maximum congestion, which is sort of the worst case scenario, and we'll define it as follows. The maximum congestion is actually equal to the maximum over all permutations pi. So this is kind of the worst case routing problem that I can imagine and that may occur in practice. So in the worst case, how can I solve it the best? So I want to find the minimum of the congestion. I want to find the minimum congestion of paths over here. And the minimum is over these types of paths. So actually, this is our solution to this routing problem. We want to find the best kind of solution for this worst case scenario. So the minimum over all solutions for these paths. So, well, for this particular tree structure, this permutation is really the worst case scenario that you can have, because every packet needs to be routed through the center over here. And it means that our maximum congestion for an arbitrary tree is actually equal to n. So now that looks really bad, actually. So we don't like this at all. So let's find out whether we can do a little bit better. And we're going to look at the two-dimensional array and see what that would lead up to. And its structure is as follows. We essentially have inputs on the left, and the outputs are on the bottom, and they are in a grid structure. So we have input 0, input 1, input 2, input 3. They all connect to their terminals. We have switches, 4 of those, and they are all connected in this grid. And at the very bottom, we will have the outputs, the output terminals. So this is output 0, and here we will have output 1, output 2, and output 3. So I notice that my circles start to resemble my squares, but these are all the switches right here in the center. So how does this work? Well, do we have a better parameter? So let's look at it together. So we need to first of all figure out what the diameter is. So what's the diameter of this particular network? So what's the shortest path between the furthest input and output? So, well, if you look at that, we can see that if I go all the way from here and I go all the way down to this corner, that looks like the largest path, and I need to cross all these wires. And in general, for any n, we will have that the diameter is 2 times n. Now, what about the switch size? It looks a little bit smaller, right? Because over here we had 3 inputs coming in and 3 outputs coming out. But over here, we see that every single switch has only 2 inputs and 2 outputs. So that makes the size 2 times 2. Now, the number of switches is pretty bad, right? Because we have n square switches. So that's really horrible. That's a lot. We would like to do much better. And what about the congestion? Do you have any idea what the congestion could be in this particular case? We will prove a theorem on that. So is there a way to map, for any permutation, is there a way to map the inputs, to route the inputs to the outputs in such a way that the switches get almost not congested? So in the binary tree, we had a congestion of n, which is linear in the switches. But over here, we can do much better. We will show that the congestion of an n-input array is actually equal to 2. So that's great. So I'll prove it in a moment, but that looks really fantastic. And so it's way better than the binary tree. Now this is really not so good, and this is also much larger, but still, we will start to think next, after we show this particular property, how to combine these two and see how we can come up with another network that's maybe that's able to combine in some ways these two properties. And maybe we can find a good solution that way. It turns out we will not immediately be able to do that, and we will need to make another step and come to the last network that really has good parameters. So what about the theorem? So if we prove this, well, how do we start? You just start with any permutation. If I want to prove something about congestion, it's defined as the maximum over all permutations. Well, let's take one of them and see what we can prove. So let's just define the path for this permutation as follows. So what we really want to do is we take any permutation and we want to find a really good solution for the routing. If that gives us a very low congestion, we're very happy. So the way to do this is, well, maybe you have an idea already. So how would I route this? So I want to connect an input I, say 1, to output 2, for example. How can I do this? Any suggestions? So of course I could go any path, but somehow I want to have some uniform structure that hopefully helps me to prove that the congestion in every switch is very small. So how could I think about this? If I make sure that, say, a packet that goes from 1 to output 2 is only going to be participating in the wires of the ith row and the pith column, then I know that every wire will only get traveled over twice by a packet. It could either be a packet that goes into this direction, or so a switch will be accessed at most twice. A switch can either receive a packet from this direction or receive a packet from the upper part. So that will be a really good idea. So let's define that. So we say that in our solution, we will design it such that the path from input I is actually going to be rightward to column pi I, and then downward to the output. So downward to output pi I. So this is a really good solution to the routing problem, because now we can continue our proof as follows. We just say, well, if you look at the switch in row I and column pi I, well, this one actually transmits at most 2 packets. because a packet can only come from the left, or it can go from the top. So either one of the two, at most those two packets will go through the switch. So this shows that we have a congestion of at most 2 for any permutation. And in order to prove equality, because that's really what the theorem says, we also have to show that there exists a permutation that achieves a congestion of 2. And that is pretty straightforward. We can, for example, use a specific permutation that maps 0 to 0 and maps n-1 to n-1. Well, for this particular permutation, when we look at the picture over here, we see that input 0 needs to go to output 0. We also see that this lowest input 3, needs to travel all the way up to here. But it's clear that the packet that needs to go over here needs to travel through that switch in the lower left bottom corner. And the input 3 also needs to travel through that. So here we clearly see that we have a congestion of 2. So now the proof is complete because we have shown this upper bound. So for any permutation, the congestion is at most 2. And we see that this specific permutation achieves this congestion. So this is the end of this proof. Okay, so that's great. So now what we like to do is we like to combine these two networks and see whether we can learn from both. So now we'll be taking out a lot of chalk over here. So the idea is to construct a butterfly network, and I will draw it in such a way that you can see the recursive structure. And the idea is to do the following thing. So let me see how I can do this the best. So I will just do the top line first, and I have the spacing. So we have input 0, a terminal. We have a switch. We have a switch. We have a switch and another one. And here we have the output 0. So the whole idea is that I'm going to combine every two outputs by using a small butterfly structure. So we have 2, output 3, output 4. Actually, I need a little bit more space. Do it once more. Output 1, 2, 3, 4, 5, 6, and the last one, 7. Okay, this is going to be pretty tight on the board. So what's happening is this. So these are all connected, of course, to switches. The switches output those. And the idea is that we create the following structure. This switch can either forward it over here or can cross it over to this particular line. And this switch can either forward it or cross it over to this line. So this is a very small butterfly structure where we have 2 inputs and 2 outputs. And we will repeat this process, and we'll do the same on each of these other levels. So we forward those or we cross them. Like this. And now that we have constructed all these smaller butterfly structures, we can start to combine 2 butterfly structures together in the bigger one. So here we had two outputs that we combined in a butterfly structure. Now we use two butterfly structures that we put into a bigger version. So how do we do this? Well, we have that the upper half over here can either forward those packets or cross them over to the bottom part butterfly structure. So for these, we can either forward them straight on, or we can go to the top butterfly. So you see that these two inputs, these two switches, either can forward packets to this sub-butterfly network or to the top butterfly network. Now we'll continue this process. And for these, we'll do the same. So we can either go straight or we go down. And over here, we can go straight or we can go to the top butterfly network. Well, now we have the final part where we combine essentially these two butterfly networks. We have two butterfly networks created here now, composed again of smaller ones. Now these two are being composed to this bigger butterfly network. Again, we take these four switches. They can route their packets forward to the top butterfly subnetwork or to the bottom one. So they can either go straight ahead, or this one can connect to the first over here, this one to the second, to the third, and this to the fourth. And in the same style, these can forward them straight like this, and then go up like this. And these are all connected because in this example we just have an 8x8 network, butterfly network. We have inputs 0 to 7. Okay. So this is the butterfly network. In a way, what you can see here, you can see sort of the two-dimensional structure, like we have rows and columns. At the same time, we can also see this binary sort of tree feeling we get from it, which is that a switch can forward its packets to either, say, the top butterfly or the bottom butterfly. So there's a split in two. The same for this one, right? This one goes either to this butterfly network or it goes to this butterfly network. So you have this tree structure sort of embedded in this two-dimensional structure. So what are the properties of this one? So let me first define like in more formal mathematics, how the switches route their packets. So how their connections are. So in order to do that, we are going to label each switch. And the idea is that we're going to label it by its row and by its column. So we will have the columns are numbered by level 0, level 1, level 2, level 3. Yes. And the rows are these integers, but we're going to represent them by binary numbers. So 0 would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then we got 1, 1, 0, and 1, 1, 1. So, for example, this particular switch would be labeled by these 3 bits, 0, 0, 1, and the integer number 1. This one would be 0, 1, 1, and its column is indexed by integer 2. Okay, so a switch is uniquely identified by its row and column. We will have b1 up to b logarithm of n, which are the number of bits to represent the row indices. And we finally have an integer L, and this we will call the level. So this particular switch either directs or routes a packet to the switch that is indexed by B1 up to, and then we get BL plus 1, and we take its complement. So instead of, if BL plus 1 would be 1, we would have a 0 here. If it would be a 0, we will have a 1 over here. But we repeat all the other bits, and we get B log n, and it routes its packet to the next level, so we will have L plus 1. Another possibility is, because there are two outgoing edges, is if we have just B1, and we just copy BL plus 1, essentially. We route the packet straight forward. We don't do anything special. We get B log n over here, and then to the next level. So for example, let's see whether we can see how this works. So for example, take this particular switch. We have 0, 1, 0. So it can either go straight on to the next level. It would go to 0, 1, 0, but then instead of level 1, we have level 2, which is the right edge over there. The other one is if this one goes up, well, we will need to switch the first bit over here, 1. We swap it into 0, and then we go to the 3 zeros over here, and we go to the next level, and that would be this particular rule. So what we can do here is to, when we see this, we can start to figure out how we can direct inputs to outputs. Okay, so let's do this. So suppose I want to route a packet from a certain input, one of these, all the way to one of the outputs over here. So the way to do this is as follows. We can just start, for example, I want to go from switch x1 up to x log n, comma 0. So I start completely at the left over here, and I want to go somewhere of my choice to the right. So I want to somehow move all the way to some other row, y1, indexed by the bit pattern y1 up to y log n, but now at the very last level, which is log n. Well, how do I do it? Well, this switch, I can use that rule up there and simply change x1 to y1. I can either leave x1 as it is, if it's the same as y1, or I can swap it to its complement, if that's the value of y1. So what I can do is I can just simply route it to y1, and then I leave all the other bits the same, which are x2, x3, all the way up to x log n. And we will have reached the first level. Now this one can go to, well, now I'm going to swap the second bit into the bit of my choice. So I leave all the other bits the same, y1 the same, x3, all the others the same. I just swap x2 into y2. So we leave all those equal. And we go to the second level. And then we go all the way to the final level, and we one by one swap all these bits. So let's have an example. suppose I want to connect, say, this one to, for example, well, let's say this particular output. So what's the binary for this one? This is actually 1, 0, 1. So if the first bit is different, I need to cross, and otherwise I need to pass straight on. So let's do this. So over here, I'm in 0, 1, 1. I need to go to 1, 0, 1. So I need to change the 0 into a 1. So I need to go down. I need to cross. Now, if I look at the second bit, I also need to change it to a 0. So again, I need to cross, which is over here. Now the third bit is equal to 1. And it's the same. So now I can go straight ahead. I do not cross. And I end up at this output. So what did I do? For every bit that is different, I cross. And for the bits that are the same, I go straight ahead. So this is how I can route packets from one input to another output. Okay. So let's look at the parameters. First of all, if we look at the diameter, well, it turns out that that's approximately equal to the number of levels, which is the logarithm of n. And to be precise, it's actually equal to 2 plus the logarithm of n. So that's great. That's a good scaling. Again, it's back to the logarithm of n. So we have the best of these two parameters. The switches that we see have 2 inputs and 2 outputs. So we again have a 2 times 2 switch. The number of switches is the number of rows times the number of columns. The number of columns is the logarithm of n, and the number of rows is equal to n. And to make it a little bit precise, it's 1 plus the logarithm of n. So that's somewhere in between those two, but if you're thinking about it, it's much better than n squared. It's almost linear, except for a logarithmic factor. For the congestion, and we're not going to talk about it here, but you have a problem set assignment that will ask you to solve this, is that actually the congestion is the square root of n, or it's equal to the square root of n over 2, depending on whether n is an even power or n is an odd power. Now, we're not going to prove that here because we want to step forward to this particular network. It's very exciting. And you will prove this in your problem set. So this one is somewhere in between these two extremes. Now, it would be really fantastic if we can somehow transform this network with a trick to, again, have a really great congestion of just a constant, like 2 or 3 or whatever, or maybe even 1. So for this particular network, in the 1960s, a Bell Labs researcher had the great idea to use a butterfly network and attach to it, again, a butterfly network, back-to-back, sort of. So what was his idea? His idea was to do the following. So the butterfly network, as we have it right now, is this particular part over here. And the idea is to now to start up mixing all those outputs that we got here together again using a similar rule. So what do? We are going to essentially repeat this particular structure on this side. Okay, so how do we do it? Well, we go either straight forward, or we start to mix them again. So it's like this output, this particular switch can either go straight ahead or can cross to the lower part over here. It goes over here, and this one goes over here. So as you can see, we have repeated this part. Is exactly the same as this structure over here. And we'll do the same for this part. So we can either cross or we can go straight ahead. We also have, of course, that these switches can go straight ahead or can cross to the top. I forgot about that. So we have this, as well. So as you can see, this particular structure repeats itself again, and we slowly start to build up and mixing all the outputs again, or the possibility at least to route them to any other row. So how do we do this? Well, we continue this particular structure now over here. So all these can either go straight ahead, that's a possibility, or they can go all down. So this switch can either go straight ahead or can go to the lower half. And for these we have a similar structure. We can either go straight ahead, or such a switch can cross over to the top, over here. Okay. So that's this. So this is Baynes' network. And then over here, of course, we have the outputs 0, 1, and all the way down to 7. Okay. So as you can see over here, this structure again has a recursive nature to it. You can see that this big Baynes network over here consists of two smaller ones that are right here in the middle. This one that goes all the way up to here. So maybe I should put a color boundary around it. Let me check how I want to do this. Right, so this particular part is again a Baynes network, and the top part in the same picture, the top subnetwork, is also a Baynes network, this part. And if you look within those, we again see a top part and a bottom part. And over here we see a top part and also a bottom part. So you see this recursive nature again reappearing. It turns out that with this trick we can completely eliminate congestion, and we can get it to only 1, which is really surprising, and that's what we're going to prove here. So this is a great invention at the time. It's really, really beautiful. So let me put in the other parameters. So they stay approximately the same up to that the diameter is about twice as large because we added another sort of whole butterfly structure to it. The switches sizes stay the same. We again have about 2 times more switches. So they sort of stay about the same up to a linear factor, like a constant factor. And the congestion, however, completely dropped down to 1. So that's what we're going to prove now. And in order to get some intuition, well, let me first write down the theorem. Actually, let me put this over here. So in order to get some insight into this, we are going to, we are going to use this recursive nature. So we're going to use induction, and we're going to say, I can really, for any permutation, I can find a really good routing for, say, this red subnetwork and for this blue subnetwork. So I know that. So what I need to do is if I have my bigger Bennis network, like this one, I would need to somehow map these inputs. I need to route them to either the top and the bottom subnetwork, one of the two, in such a way that there will be absolutely no congestion, because we want to keep this one. So a switch should only see one packet coming in. So that means, for example, and we'll come back to that, for example, for this switch, it should not receive a packet from both this input and from this input. So the intuition that we are going to create is we're going to create, like, we're going to list our constraints, the constraints that we need to satisfy, like the 0 and the 4th input should not both be mapped to this top subnetwork, and so on. So we will get into that, and then we will gain a lot of intuition on how to solve this. Okay, so what's the theorem? So the theorem is that the congestion of the n input Bennis network is actually equal to 1. And we will prove this for n equal to a power of 2. We have assumed that at the start with all the other networks as well. And in this case, we will use induction on A. So that's the method that we will do, because that's also the recursive structure of the Bennis network itself. So we will use induction on A, and we're going to define the induction hypothesis simply as the theorem is true for A. Okay. Now let us do the base case. We always start with the base case, and that should be pretty easy, because this is the most basic Bennis network. So n equals 2 to the power 1. We essentially have 2 inputs, an input 0 and an input 1. They are connected to these switches over here that can either forward them or can cross them over, and then they go directly to the output. Notice that in this case we just have the most elementary butterfly network. It's the same. So we have output 0 and output 1. So this corresponds in this picture to these little small things over here. This one and this one and this one over here and the 4th one over here. So now let's take any permutation. We want to show that we can route it in such a way that there's only a congestion of 1. So let's do this. So there are essentially only 2 permutations. Either 0 is mapped to 0 and 1 is mapped to 1, or 0 is mapped to 1 and 1 is mapped to 0. So in both cases, we can just route them through their own switches. So we have that either pi of 0 equals 0 and pi of 1 equals 1, in which case we just direct them straight through. There we go, straight through, and every switch only sees a packet once. So for this particular permutation, we have a congestion of 1. Now the other permutation that we can have is if 0 is mapped to 1 and if 1 is mapped to 0. Well, in that case, we just route this cross over to the bottom row, and here we go from this switch to the top row. Again, every switch only sees a packet once. So in this case, in the base case, we are done, we are happy, we have shown that the congestion is equal to 1. So now we get to the harder part, because for the inductive step, we are going to assume, of course, that it holds true for a smaller Bayes network. So we assume that PA is true. And, well, let's try to gain some insight here. So we know that within each, from our induction hypothesis, within each subnetwork, we can achieve, we can solve any routing problem with congestion 1. And for this subnetwork, the same. That's our induction hypothesis. So how do we go ahead? We need to somehow map these inputs according to the permutation of our choice. So that could be, for example, input 0 goes to output 5, or input 1 goes to output 2, etc. So somehow we need to choose where we are going to map this particular input to. So the packet that goes, packet 0 that comes from this input, should either go to the red network or it should go to the blue network. And for each of these inputs we can make such a choice. But we have to be very smart about it, because we need to avoid any congestion. So the intuition is that we're going to set up a constraint graph. A graph that represents all the constraints that we need to satisfy in order to achieve congestion of 1. So let's do an example such that we can figure out what's going on. Actually, let me put it over here. So just take an example permutation, and we'll go through this example and then see how the proof works. So let's, as an example, have pi of 0 maps to 1, pi of 1 maps to 5, pi of 2 goes to 4, input 3 goes to 7, 4 maps to 3, 5 to 6, 6 to 0, and 7 to 2. So this is just an arbitrary permutation. And okay, so what do we see? We want to make sure that, for example, this switch is only seeing one packet. So it cannot see a packet both coming from input 0 as well as from input 4. I cannot see that. I do not want that to happen. Similarly, for this one, I do not want to see a packet coming from 1 or one from 5. So let me define a constraint graph that sort of represents this. So the constraint graph that we are interested in is defined as follows. If two packets must pass through different networks, subnetworks. So in our case, the red and the blue subnetwork. Then we'll actually have an edge between those two. So then there is an edge between them. So for this example, we're going to set up this constraint graph. And so I was just talking about this particular switch. It cannot see one coming from 4 and a packet from 0. So what we do, we have an edge between 0 and 4. In the same way, we have an edge from 1 to 5. Why? Because a packet that comes from input 1 and a packet that comes from input 5 cannot both be routed through this switch, because then the switch would see 2 packets, and then the congestion would not be 1 but 2, right? So 1 and 5 also have an edge in between. And in the same way, we have 2 and 6 and 7 and 3. So 2 and 6 are is this constraint, like 2 and 6 over here, and 3 and 7 is the other constraint. So if I have those constraints in place, well, then I know that the routing that goes from level 0 to level 1 will not violate my congestion of 1. So that's great. Then I hope to be able to use the induction hypothesis, and I get a proper routing within the red subnetwork and one within the blue network. And then I need to map all these to these outputs. So I also have constraints on these outputs because, well, for example, take this particular switch. It should not see a packet coming from this particular one and one from this one. So how do I code that up? So, okay, so let me first write out what we did here, and then we'll do the same for the last level over there. So, oh no, that's not really necessary. Okay, yeah, so at the output side over here, we have similar constraints as we did over here. And in this particular example, just as an example, suppose we look at the packet that is destined for output 0. Well, what is this packet? Well, I know that pi of 6 is equal to 0, according to my example. So packet 6 is destined for this particular output 0 over here, and goes through this particular switch. So this packet, and also the packet for output 4, which is, if you look at the mapping, pi of 2 is equal to 4, so that's packet number 2. Well, both of these packets cannot pass through the same subnetwork. Cannot pass through the same subnetwork. So why is this? So let's look at this particular example. So output 0, well, comes from packet 6, somewhere over there. Now suppose packet 6 was routed through the red network, and at the same moment also output 4, the packet that is destined for output 4, which is packet number 2. Suppose packet 2 was also going through the red network. Well, then I notice that both of these packets must arrive at this particular switch in order for one to be routed to output 0 and the other one to be routed to output 4. So in order to avoid congestion in this particular switch over here, we need to have a constraint. The constraint says that the packet for packets 2 and 6, that those two cannot go through the same subnetwork. So we essentially have another edge over here. We already had the constraint, but it's just the same edge. So let's look at the other constraints that we have. Well, for example, well, let's look at a different example. So, for example, if I look at this switch, well, it can, if a packet goes through here that needs to end up at 1 and a packet that goes to 5, if those two packets are routed through the same red subnetwork, they have to end up here in order to go to both here and to there. So I have congestion of 2. So what are those packets? Well, what does pi map to? To 1 and 5. Let's look over here. We see that pi 0 is equal to 1, and pi 1 is equal to 5. So packet 0 and 1 are actually mapped to output 1 and 5, and they should not go both through the same subnetwork. Okay, so we have another edge over here. And now we can continue this. And we have 5 and 7. So just have a look over there. Say 5 and 7, they map to the outputs 2 and 6. Again, we have 2 and 6. If they are both mapped to the same network, this one, for example, then I will have a problem. Okay, so the other edge is over here. Okay, so what did we do here? We started to write out the constraints on this side, and we wrote out the constraints on this side. So I only looked at the red subnetwork. That's what I realize now. I could also have looked at the blue network. So let's do that also, just to make the picture complete. So for example, let's look at this particular example. The packets 6 and 2 should not both be routed through the blue network, because then they would both have to go through this switch. One going up to output 0, and one going to the left, to the right, to output 4. So in order to avoid congestion at all costs, we have this constraint graph. So now we come to the key insight. And the key insight is to use a two-coloring of this graph. So the key insight is a two-coloring of the constraint graph, which will lead to a best solution for the routing problem. Okay, so let's do this. So we will color this one blue. As you can see, this is an even cycle. Blue, red, blue, red, blue, and red. We'll make this one blue and this one red. Well, it turns out that we can now start our routing process. So for example, actually I will draw a new graph to make that really clear. So I have my blue and my red chalk over here to demonstrate what I mean. So what do I do? I have 0, 1, 2, 3, 4, 5, 6, and 7. I have the switches that correspond to those. Well, if it's colored red, so 0 over here is colored red, I will direct it to the red subnetwork. So where is this red subnetwork? It's really contained over here. And the blue one, so this is the red one. And the blue one is right here. And over here we have the outputs, ranging from 0, 1, 2, all the way to 7. Okay, so input 0 is colored red. We go straight ahead. We want to go to the red network. Input 1 is colored blue. It goes, therefore, to the blue network. So this is the only way how to do it. Input 2 is colored red. Go straight ahead. Input 3 is also colored red. Go straight ahead. Input 4 is colored blue. Goes to the blue network. Input 5 goes up to the red network. Input 6 goes straight ahead to the blue network, is colored blue. Input 7 is also colored blue. Okay, let's look at the outputs. So, for example, well, let's have a look at output 0. So output 0, which packet is mapped to output 0? It's packet number 6. So 6 was mapped into the blue network, and then it needs to be mapped to output 0. So it's only one edge that goes from the blue network to output 0, which is this particular one. And then somehow this one needs to be mapped to this one over here. Now we can continue like this. Output 1 should receive a packet from, let's look at the permutation, from 5. So, output 1, pi of 0 is equal to 1. So packet 0 needs to go to this particular output. Now packet 0 is in the red network, so there's only one edge that goes from the red network to this output. So we need to have a connection over here. Now we can continue this and note and demonstrate, and you can test it for yourself too, that output 4 needs to receive a packet from the red network. Actually, it should be this particular one, which happens to be packet number 2. And then we have this one, right. So let me just finish it. We have this, and we have these two, and we have this one, we have this one, and we have this one. This one goes straight ahead. This one goes all the way up, and this one goes all the way up. So what do we see? We see that packets over here, that these switches only see a packet once, and these ones as well, these one also, and these ones also. So we have directed the packets, routed the packets to the red and the blue sub-networks in such a way that the congestion at the last level and at the first level is still equal to 1. Now we use our induction hypothesis, and we conclude that we can map the route, that we can have a routing from packets from here to here, such that the congestion within the subnetworks is only 1. So within the blue as well as in the red. So this is the insight into how this works. And I notice I'm running out of time, so the formal proof we will have to postpone till recitation. But that's actually really a very simple thing to do that right now, to just keep this key inside, and then you can easily prove the theorem. So, but this is the real insight. Thank you.